Okay, so at the last lecture, we introduced a different method called conjugate gradient. And that's actually all the gradient-based method I'm going to cover in this course. Today, I'm moving on to a different area. So today, we are going to cover constrained optimization. So after today, you will know how to handle optimization with constraints. Okay? So, in the past few weeks, we never talked about constraints. So I want to remind you, for our optimization problem, we are trying to minimize the objective function subject to constraints. So usually we use G for inequality constraints, H for equality constraints. So this is so-called a constrained optimization. Okay? So there is the simplest method for constraint optimization, which is called linear programming, so-called the LP. Okay? Today we're going to cover how to do LP. Before we start, we need to know the standard format for nonlinear programming. We have to convert the entire problem to certain format so linear programming can solve it. So it's very important for linear programming to have a standard format. So, first thing you need to do is to linearize all functions. So what is the best way to linearize the functions? Something we have done so many times. What is the best way? If you have a nonlinear function, what is the best way to linearize it? Some kind of approximation? Taylor expansion. Yeah, just use Taylor expansion to approximate the function. So basically you use first order Taylor expansion. Okay? So we can only handle linear functions. LP cannot handle nonlinear functions. So let's assume you already know how to do it. If you forget, I will remind you. So any function, if that's nonlinear, if you want to linearize it, you need to choose an expansion point, and then you can do this. Okay? That's linear approximation by Taylor expansion. You don't keep the higher order terms, just keep the first order terms. Okay? So, second thing is, nonlinear programming doesn't handle inequality constraints. We need to convert all inequality constraints to equality ones. Okay? So basically, we need to convert all the G constraints into the forms of H. Every constraint has to be having the equal sign. Okay, so how do we do that? So, I will show you two kinds of variables that help us do that. But the reason why okay. Before I start to introduce that part, I probably need to show you what is the expected final form. So when you do the conversion in step 2, you would know what to do. So I need to talk about the third step first, the general format for LP. Okay, so we have to solve the linear programming problem in the following form. Basically, a C dot X. So C1x1 plus C2x2 plus da 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 Cn. Okay? Subject to, now we can only handle equality constraints if we complete the step 2. And we are going to write in the following form. It's a A matrix dot product with X equals to a B vector. Okay? And this can also be written as A11, A12, da da da, A1N, A21, A22, da da da, A2N, da 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 da, AM1, AM2, AMN. Okay. Times the vector x1, x2, da da da, xn equals to b1, b2, da da da, bm. Okay? So, what are those? They are basically A11 x1 plus A12 x2 plus da 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 A1n xn equals to B1. You know the rest. Right? Basically, they are linear functions. You can have many of them. Okay? So now you have n variables and m constraints. One question. What will happen if n equals to m? What will happen? Anyone? If you have linear equations, m linear equations with n variables, and the number of m equals to number of n, what will happen? Say again?
It has inverse because it's square.
No, something even easier. You know this when you are in junior high school. No, that's not what I want. Yes, only one solution. Yes. If you have n variables, n constraints, but they have the numbers are the same, you only have one solution if it's solvable. Right? So if n equals to n, and also it's a solvable problem, solvable. then you only have one solution. In that case, do you need optimization? Anyone? No. Because there is one solution. Just solve the matrix AX equals to B. So X equals to A inverse times B. Solved. Right? So in this situation, usually you don't need optimization. How about n greater than m or n smaller than n? So if you have a lot more variables than the number of your equations, what will happen? So usually we say this is under constrained, and this is overly constrained, right? So if you have a lot more equations defining defining the relationships between fewer variables, you are overly constraining the situation. But if you have a lot more variables than the number of equations, that means you are under constrained. So if you are overly constrained, sometimes, if you're not lucky, most of the time, you don't have solution. Because maybe, for example, if you have 3 variables and 5 equations, maybe 3 out of the 5 can already determine one solution. But the other 2 extra equations doesn't satisfy the solution you found earlier. So those 5 cannot reach to one agreement of one solution. In that case, no solution, right? But in the other case, if you have 3 variables but only 2 equations, that means you cannot basically have multiple solutions, multiple possible solutions, because you don't have enough equations to confine the values. So in the situation of number of variables larger than number of equations, you should have many solutions most of the time. So which one needs optimization? Case 1, case 2, or case 3? Anyone? Case 2, yes. Because you have so many solutions, you have choices. So one of them probably is the best. So we're searching among those possible solutions and trying to find which one is the best. So we usually handle this situation. In the future, if you try to solve constrained optimization, make sure you realize this, okay? Hold on, am I right? Ah, yes, I'm right, yes. Okay, now, back to the standard format. There is one more thing I haven't talked about. Not only you need to satisfy those equations, we also need to satisfy some other things. We want all the variables to be positive, and also we want the coefficient on the right hand side to be positive. So all the variables has to be positive, all the b's has to be positive. Okay, that's special rules for linear programming. And I will let you know later on why. Okay? So standard format is like this, and usually your number of variables is greater than the number of your constraints. And now we need to figure out how to do the step 2. When you have inequality constraints, how do you convert them into equality ones so it is satisfying what you are looking for in the step 3? Okay? So let me talk about step 2. So back to step 2. Let's say I have one equation like this. I want to convert this into an equality constraint, but it still remains this. Basically, after I do the conversion, whatever I have at the end has to be equivalent to what I had at the beginning. This conversion has to be equivalent. So we are going to introduce something very interesting. We're going to do this. On the left-hand side of the equation, I'm gonna say plus S1. And on the right-hand side, I'm gonna say equals. And we are keeping the coefficient on the right-hand side, the constant on the right. So we add one more variable on the left-hand side. This is called the slack variable. Okay? And the slack variable has to follow a rule. S1 has to be positive or 0. So let's plug in some number and see what's going to happen. If slack variable equals to 0, then this part equals to 3, right? If S1 is positive, then this part plus some positive value equals to 3. So this part, the double line part, would be smaller than 3. So when you convert this equation into these two new equations, if they satisfy at the same time, then you still have 3x1 plus 2x2 smaller or equals to 3. This is how you can convert one equation into two, but converting inequality into equality. Okay? Everyone okay? Now, there's another situation where you have this. When you have larger than, what do? We're going to do something similar, but this time you are going to minus, so T1, okay, we're using T this time, and equals to 3. So this T is called a surplus variable. Okay, and T also is positive or equals to 0. Now, again, let's try to plug in some number into the new equation. If T1 equals to 0, 3x1 plus 2x2 equals to 3, right? When T1 is positive, when this guy is positive, then the double line part has to be larger than 3 so that this equation is valid. So at the end you realize the double line part is either equals to 3 or larger than 3. That's why it's still equivalent to what you had earlier. Okay? Making sense? So you can either introduce so-called the slack variable or surplus variable into your equation and convert the inequality sign to equality sign. Then you satisfy what linear programming wants you to do. Now, one more equation. One more question for you. What if this is happening? What if on the right-hand side that is negative? What do you do? Because if you follow what we introduced earlier and introduce slack variable over there, then on the right-hand side of the equation is going to be negative. We want the b's to be positive, right? So what do? You can easily multiply by -1. So at the end, you have something like this. Just multiply -1 to switch the sign. Then add the surplus variable. So it's like this. Minus, for example, T2 equals to 0. But T2 has to be positive. Okay? So you still can do it. Okay? Now, let's assume you already know how to do the 3 steps. Hold on. Turn off this. Okay. So first, if you have a general optimization problem, you convert them into linear equations, and then you are going to convert the inequality ones into equality ones, and make sure you form a problem like this. How about a special situation right here? Oops. How about x has to be positive? What if you have a design where you allow your variable to be negative? You can do some variable shifting. So for example, here's an example. For example, you have some variable called y. It can be larger than -5. And it could be smaller than 10. So if you use this variable for linear programming, you will have a problem because your y can be negative. Then you can define a new variable which is called x, and x equals to y plus 5. Then plus 5 on everything, you then have y plus 5 is smaller than 15. So in the end, you have positive x. Basically, you have a variable shift by 5. And at the end, once you get a solution, you get optimal solution of x. You just convert it back. Then you know y equals to x minus 5. Okay, so you basically solve as using the variable of x, but at the end, to solve for y, you just plug in back to the same equation. Okay, so still, if you allow negative variables, you still can do linear programming. Or you can separate the design space. You can cut the design space into half. Solve for the positive side and then solve for the negative side. If you allow x to be any value within the real number space. So probably what you can do is you choose x equal to positive and then solve for the positive side, and then reversely solve for the negative side. That's also another way. And see which solution gives you the best. Okay? So let's get back to. So let's now assume you already have the standard format. Now we have to figure out what we can do. So I'm going to define certain things. You might not understand what's going on, but you just need to follow what I introduced, and later on you will know why. Now I would like to write down the standard format again. So we have minimize the vector of C dot product with X subject to a matrix of A dot product with your vector X equals to B vector. Okay? If I rewrite it as a matrix multiplication, then it's like a C vector transpose X, and this is like A multiplying X equals to B. If you enjoy matrix multiplication, then this is what you have at the end. So if we check the dimension of everything, X is a n by 1 matrix. X is n by 1, right? And I'm writing n by 1 here. So C is supposed to be n by 1 as well. When you transpose on the right hand side, then it's gonna be 1 by n, right? So at the end, this is just one scalar, one value. Makes sense? Your objective function is supposed to be one value, right? It's gonna be 1 by 1, so it's a number. How about your A matrix? So let's get back to here. A is m by n, m by n. Okay, so at the end, it's gonna be m by 1. So B is m by 1. So here the same thing, m by n, m by 1. Then we know which one is larger. N is larger. N larger than m, right? So if we draw the size of the vector, if you make a drawing of them, C is like C transpose is like a horizontal vector. So the size of this is the length of it is n, and multiplying a vector, a vertical one, and the size is n, right? So it's like a horizontal vector multiplying a vertical vector. So this is what happened for the objective function. How about the constraint part? Constraint is m by n. So it's gonna look like this. Here also the length of n, but over here is a length of m, and n is a smaller number, so it's gonna be like a flatter matrix. And over here, the size of this is n, and this is gonna equals to a vector that is shorter and the size is n. This is how it's gonna look like if you try to draw the size of the matrices. Okay? So right here we're going to do something. We're going to separate the A matrix into half. Actually, we are going to do the same for C matrix. So this is my C vector, actually, C transpose. This is my A matrix, right? We're going to separate them into half. The way we separate is gonna be like this, okay? And I'm going to choose, hold on. Let me make it nicer, more accurate. Okay, I'm gonna pick up this area and keeping the width of M. So over here, this is N minus M. Okay, I'm gonna do the same thing for C. So over here, there are M components. The rest will be N minus M components. Just like placing a separator between the in between. And I'm gonna give some names to those. Here I'm gonna call this A with a small b and A with a small n. So from now on, small b, do I use large b? I think small b is okay. So the how do you call that? The index b means what? Means so-called the basic variable. Okay, and index n is going to it's not an index. It's actually a subscript, not index. Because index represent numbers. So n is gonna represent so-called the non-basic variable. So there are going to be basic ones and non-basic ones. And of course, you have no idea what's this for. So I will tell you what this is for later on. And for the C, since we already separated them into two, so over here this is gonna be CB and CN. And of course, it's the transpose of it. Okay? And even for the X, we can separate into two. So the length of this part is N, this part is N by M. Same here, length is M, and here is N by N minus M. So in this case, the upper part is gonna be XB, lower part is XN. Okay? I'm not going to repeat at the bottom. If we do that, what happened? If we do that, we can rewrite the equation into the following. We are basically doing CB dot product with XB plus CN dot product with XN. Or if you don't like dot product, basically transpose. CB transpose XB plus CN transpose XN. Okay? Subject to what? A matrix B, the product with XB plus A matrix N, the product with XN equals to the same thing, B vector. Or if you don't like the transpose sign, it's the same thing. For matrix multiplying vector, the dot, you don't really need to write it. Okay. Now, why do we do this? Because we don't know where the solution, what is the solution, so we usually need to start with an initial guess. And the trick of linear programming is that it's gonna start with making a guess on the non-basic variable. So we're going to guess xn equals to 0. So basically, everything inside xn is gonna be 0. So it's actually a vector of 0. All of them are 0. If we do that, what will happen? It's gonna be like this. So basically the xn becomes 0. Then you have ab times xb equals to b vector. And what's the size of ab? It's a m by m matrix. And this is the xb part is m by 1. So at the end, b is still m by 1. So this can be solved directly by taking the inverse, right? So if you guess xn equals to 0, then xb part can be solved. You get a solution of xb. However, it's just a guess. Only if you are super lucky, then this is a solution. Of course, it's not the best solution. You haven't shown anything that this is the best. How can you say it's just one feasible solution? This is just one feasible solution. What do you mean by feasible? With the determined xb and zeros in xn, you know all the x. So all the x is gonna satisfy your equality constraint. If you have a series of values that satisfy your constraint, it's a allowable solution, but it's not the best. Not yet the best. It's just a feasible point. Okay? So it only tells you it's feasible. So, what do we do? So we're going to check on xb. We're going to check one equation. How does xb look like? So it's important we're going to check what does xb look like. Okay? So from this equation, we can determine xb in a certain way. Basically, it's gonna be a b inverse times b vector minus a n x n. Okay? If you expand it, it's gonna be like a b inverse b vector minus a b inverse a n x n. We're going to check. We're going to rewrite xb. Okay. Then, if we know what xb look like, we're going to plug this form back to our objective function. Then we're going to check our objective function. Our objective function is this one. We're just plugging in. So when you plug in, here's your CBI, yes, CB dot product is fine. And then your xb is already written in the earlier form. So AB inverse dot product B minus AB inverse dot product AN dot product XN. Just plug it in. And you keep the same thing for AN. Okay? Now let's expand the whole thing. So it's going to be like CB AB inverse B, small b, minus CB AB inverse AN dot product XN plus CN dot product XN. Okay? So here we do see some common terms. We do have dot product of xn on the right hand side of the second and the third terms. We're going to combine them. Okay? We're going to combine them. So CB AB inverse B. Here I would like to start with plus, and over here it's gonna be Cn minus CB dot product AB dot product AN, and the whole thing dot product with XN. Okay, we're just combining the coefficient in the front. So what's interesting about this is that if we check on the first term, CB is a vector of the coefficients in the objective function. So basically, your objective function has a bunch of C1, C2, and C3. There are just several C's. AB is also some coefficient inside the constraint. You have A dot x equals to B, right? So A are just a bunch of coefficients. So over here, AB inverse is a matrix of numbers. How about the small b? Small b is the right hand side of the constraint. So also a bunch of numbers. Right here you realize this term, CB dot AB inverse dot small b equals to something, some value. It's just constant value. Okay? So in this case, if you try to do optimization, this part won't change if you try to change your variable. Okay? So what you can do is your right hand side, the second term. Okay, now remember we want all the variables to be positive or zero. So right here, your xn could be some number by, you can change them as long as they satisfy your constraint, but they have to be positive or zero. So if I want to decrease the objective function, what I'm looking for is, I hope the coefficient right here has to be negative. I want this coefficient to be negative. I should say 1. If you have some coefficient right there is negative, multiplying some values in xn, that will decrease f. Right? So the goal is, we're trying to figure out how we can make our objective function value the lower the better. So actually we want to find some kind of coefficient inside this chunk and see which coefficient is the most negative one. So we are looking for one of the coefficients here that is the most negative. Very important. Choose that one. We only pick up one of it. Why do we do that? Because initially xn equals to 0. At the beginning, all the xn, they're just 0. So no matter what coefficient it's having in the front, it doesn't matter because all the xn's, they're 0. But we're going to pick one of them inside xn. We're going to pick one. And the one we pick is going to have a coefficient in the front, and the coefficient has to be the most negative one. So when we pick up that index, that particular one, and we're going to allow that variable to have numbers, not 0. We're going to increase that particular x. When we increase the value of that particular x, because the coefficient in the front is negative, it's going to decrease the objective function. But we don't change all the variables at the same time. We only change one variable at a time. So we are going to pick up the one that is having the most negative coefficient in the front. Okay? So, before we continue, I want to check on the dimension of this chunk. So let's do this. Cn is n minus m. So this is it's a vertical. It's a n minus m by 1. CB is m by 1. AB is m by n. Even its inverse is m by n. AN is n by n. Okay, n by n minus m. Okay, I just want to check on the dimension of this at the end. What is xn? Xn is n minus m by 1. Okay? So if you check on this, you realize xp is what? n by 1, yes.
I think Cn should be 1 times n minus
No. xp is n by 1. xn. Yeah. Which one is wrong?
Cn should be 1 minus times n minus m.
Which one?
Cm and Cb is
No,
yeah.
I'm using transpose. I'm using dot product, so it's gonna be vertical, right? Dot product is vertical. One minute. Yeah. This is actually right. It's sometimes it's confusing if you are using dot product. So if I show you over here, if I use dot product, if I use transpose, then it's gonna be CB transpose AB inverse AN, but the whole thing needs a transpose so that you can multiply with xn. That's why it's very confusing. So if after transpose, this is 1 by n minus n, this is n, okay? So these two multiplying with each other is gonna be 1 by 1, some number. How about this part? CB transpose is 1 by n, this is n by, sorry, this is n by m, this is n by n minus m. So the whole thing right here is going to be 1 by n minus m, but you need to transpose this, so in the end it's gonna be, do I transpose this? Oh, no, you don't. Do what?
Oh, that should be m times n.
You don't, because you just transpose the first one. Sorry. You don't really transpose it. Because an is a matrix multiplication with xn, so you don't transpose it. You can already multiply it like this. It's a horizontal vector times the matrix times the matrix and then times the vertical vector. Okay, so
Sorry, bro.
yeah?
It's not from the FAN dimension. I think it should be m times n minus n, not n.
An? You mean it's...
Yes.
Yeah. This is m, you're right. Sorry. This is yep. So at the end, these two multiplying each other is 1 by 1. So what's inside the bracket? It's 1 by n minus m. It's like a horizontal vector, okay? And there are multiple components inside. If you say, let's say you have 5 variables, and if you have 3 constraints, then in this case you have a 1 by 5 minus 3 vector. So you have a 1 by 2 vector. It's like 2 values. So it's going to be like a value 1 and value 2. They're going to have 2 values, and they could be different. You need to choose the most negative one from those 2 values. Okay, so your xn at this point, this will be the first one of your xn, and this is your second one of your xn. So at the beginning they are 0. So it doesn't matter what coefficient they have in the front. Let's say, just for example, this is -5, this is negative 2. So if I allow xn to have values larger than 0, so if I increase the value of xn, the first xn, so if I convert it to xn1 equals to 1, in that case, the whole thing becomes -5, right? Because originally x was 0. If I allow xn1 equals to 1, the objective function becomes -5. So I decrease the objective function. The goal is to minimize f. So I need to know, should I increase xn1 or xn2? If I increase the second one, I allow this to become 1. In that case, the objective function only decreased by 2. So it's a slower decrement. For linear programming, we want the objective function to decrease faster. That's why we want to pick up this one. It's the most negative one. And this one is going to be the variable we pick, and later on we allow this variable to have numbers greater than 0. Okay? So allow this variable to be larger than 0. The idea is like this. Okay, so later on when I show you how to do the iteration, I'm going to check this chunk. And then in this example, you will see a horizontal vector with multiple numbers. And inside this horizontal vector, I'm going to choose the most negative one. And the corresponding x is going to be the variable that is no longer to stay as 0. I want to increase its value. And later on, that variable will become positive. If I do that, I'm pretty sure my objective function will be decreasing and decreasing. I will keep on doing this until I cannot improve anymore. Okay? So that's the first step of linear programming. Now, if I already pick up one variable, I want the variable to increase its value from 0 to certain positive value. Whenever I do that, I need a constraint to be satisfied, remaining satisfied. Because earlier, when I said I wish my non-basic variables are 0, I can use this equation to solve for the basic ones, right? And that's one feasible solution. Now, if I change one of the xn from 0 to a different value, then that changes everything. That all the other x will be changing. So the idea is, now if I pick up one of the xn, so I'm going to pick up one of the xn. I want to convert 0 to some value. Pick up one of the xn. Increase its value from 0 to some value. When I do that, I want to pick up another one inside xp. And I'm going to allow this value to decrease. It will be some xp will be some value, but it is going to be positive. I want it to be some positive value and then decrease to 0. So 1 is going to be converted from 0 and then upgrade to some positive value, but the other one will be decreased from its original value and then drop to 0. So it's going to be some process like that. And I'm going to tell you why we can do that. So in order to do that, I need to copy this equation. Basically, this is the equation that we pay attention to, starting from the second part. So over here, because we already choose one of the xn, later on it will become positive. So we can do this. We can rewrite this equation in the following form. I'm gonna say xn, and I'm gonna let me see how I'm gonna call this. Let me just say the chosen one. Okay, I'm not sure which index I'm gonna use. No, maybe not the chosen. I'm gonna, let me see, just double checking how I'm going to use it later on. A is going to be, I think it's J, okay? I'm gonna call this J. So the Jth component in, let me give myself some space. Okay. The Jth component in Xn is chosen because it has the most negative coefficient in the updated function. Okay? Let's say the jth one was chosen. So I'm gonna call the jth one as xnj for now. So once I do that, we know our an is a m by n minus m, right? So only whatever that matters inside the A matrix is gonna be is multiplying basically the jth column. So inside, what matters is the jth column. So what's the best way to say this? Over here, maybe I make a drawing of it. So originally A matrix looks like this. This is m by n. Over here, this is m by n. This is n minus n, right? So A matrix, this is an. This is am, right? No, not A basic and A non-basic. The A non-basic is a horizontal matrix. So what matters the most is actually the jth column. Because only the jth column will multiply jth column will multiply with x and j, right? Well, to be complete, I actually need to draw the vector as well. The rest are just zero. And here we don't care. We only care about the jth column inside an, and it's gonna multiply with x and j. And x and j is going to become positive later on. Okay, and this remains the same as b vector at the end. This is supposed to be like this. So when we have this, we are going to use convert this into the following form, because we already know xn, the jth one is chosen. And this one will be converted from 0 to some positive value. So basically, it will be converted from non-basic to basic. Because the non-basic ones, they are 0. I convert this one to be basic later on. So in that case, I need to choose one from xb and convert it from basic to non-basic. So what does it mean? Which means its value reduce to 0. Reducing, if you're picky about grammar. Right? So the next step is to figure out which xb will be chosen, and that xb has to become 0. So to do that, we are going to rewrite the equation into the form of xb. So xb equals to AB transpose, let me see, plus A, and then AN, XN, AB transpose B, right? Okay, so because I care more about the XP, so I want to have I want to observe the XPs. So for easier evaluation later on, we're going to call this and this into a new form. I'm going to call this A hat, and I'm going to call this B hat. Okay? And for the A hat and B hat, we let's check the dimension first. So AB is an m by m matrix. AN is m by n minus m. So A hat is m by n minus m. Here B hat basically m by m, m by 1. So B hat is m by 1. Okay? And here, if I make the drawing again, this is A hat, this is n, this is n minus m, and here is your xn. xn is in the size of n minus m, right? And we said the jth one is chosen. So only the jth column matters. Okay? So inside the A hat, every component inside is going to call A hat ij. Okay, A hat ij. So we're going to check A1j, A2j, A3j. They are going to multiply with the jth one in xn. So on the right hand side, I think the best way to show you probably is to write down. So this is gonna be the matrix, and this is the jth column. Then you have A hat, 1j. Well, I better have a larger space for this. I need a larger space. So if I draw this larger, make this larger, okay? So this is m by n minus m, and here is your jth column. The first one is A hat 1j, second one A hat 2j, da da da, A hat mj, okay? And for here, this is 1 by n minus m. Then the first one is going to be B hat 1, B hat 2, at the end B hat supposedly m, because B hat is m by 1. And over here, we only care about x and j, right? So basically, but don't forget about the front. You have a xb plus. Okay? So if you write down all the equations, actually it's like this. xb1 plus A hat 1j xnj equals to B1 hat. xb2 plus A hat 2j times xnj equals to B2 hat. Da da da. X B has m of them. The m1 plus A mj hat x and j equals to b the nth one. Okay? So actually, they are n linear equations. Okay? So at the end, I'm going to originally all the xn's were 0. Now I want to increase the value of xn. And in order to make this equation satisfied, supposedly the xb's needs to reduce. Because something on the right hand side increase, then something on the left hand side is supposed to be reducing. But is it always true? Actually, later on I can show you one example. I can make a drawing like this, and this is going to be the jth x, and initially the x and j is 0, but xb m's, they are not 0. So there are several of them. So this could be one of the x, this could be the other x, they could be some numbers. This is just illustrating the idea. And all the xb's has a linear relationship with x and j. They are linear relations. So the linear relation could be something like this, could be something like this, could be something like this. Oh, I don't want to draw at the same position. Okay. So their linear relations could be something like this. Now, if I try to increase the value of xn, that means whenever I increase a little bit, all the xb's will change its value. They have to stay on those linear lines, so we are always keeping the constraint satisfied. We're always feasible, stay feasible. So how much can we increase x and j? We will be increasing this until we reach this point. So when x and j was increased up to that red circle, then you realize this particular variable will drop to 0. But the other variables remain positive. So at this point, x1b remains positive, and xb1 remains positive, xbn remains positive. Only xb2 drops to 0. So that's the one. That's the one will be reduced from its original value to 0. And x and j will be the one originally was 0 and then now increased to certain value. So the idea is we need to pick up the 1 from xb, that one reduced to 0. So we are going to do something so-called the ratio test. Actually, it's like finding the slope that drops the fastest. So we usually call this ratio test. And inside ratio test, we will be checking all the b, here I'm gonna say I, over all the a hat ij. Okay? We're going to do that. There are many of them. So we're going to check those for all i's. And you will end up with a bunch of values. After that, we are going to choose the smallest positive one. So it has to be positive and it has to be the smallest. Okay? What function has the steepest dropping speed, which is when this ratio is positive and is the smallest, then it drops the fastest. Okay, you can later on play with it. So basically, we're going to choose this ratio and find which one is the smallest positive. So for that particular I component, so pick up this BI that has the smallest positive ratio. Then that one will be convert from basic to non-basic. Okay? We will be, when we are done right here, is the end of one iteration. we will go back and repeat everything again and again until we cannot do it anymore. So this is actually end of the iteration. Then we're going back to do the exact same thing again and again. So you may feel weird. Hey, how come this can help me find the optimal? Let's try one example. So now it's time to try one example.
Professor.
Yeah, go ahead.
I want to go up first. I want to ask something. Is that really n minus n on the matrix? I think it should be n or is n minus and on the B1 hand, right?
You mean this guy?
The right one. It should be n or n minus n.
Let me see. A hat. Are you talking about
not
A?
that one. In the below. That one. Equal to.
This holding?
Yeah. But the equal to. It should be n or n minus.
Let me see. XB.
It should be n or minus. Only n or n minus n. Because in the before it should be n times 1, right? The result of it.
Okay. Over here, which
Yeah.
number is wrong? It's hard to which number is wrong?
But
Oh. Let me see. You're right. It's n by 1. Yes, it's n by 1. You're right. Thank you.
also, I just want to know, is that the transpose of AB is equal to the inverse?
Transpose of AB is it's a square.
No, I mean, is that equal to the inverse? Because you say when you write,
AB may not be the same.
because you say when you write AB minus 1, you say AB transpose, so I got this on that.
Oh, you mean right here?
Not that one. This one. Because this
Oh, you
one.
know.
When you describe this one, you say this
Oh.
is AB transpose, so I confused.
Yeah, because it was from this equation. You multiply AB transpose to everything, then you will get this. Right?
Okay.
Yeah.
So it's from there.
Derive from there. Yeah. Okay. Thank you for pointing out. So if you derive from there, you will get this. Okay? So we really need to do one example, then you know what's going on. Now, one example. Let's try to minimize negative x1, negative x2, subject to so here's the linear constraint problem, right? First, let's check on the right-hand side of all the inequality constraints. They're all positive, which is good. So they are positive, which is good. So we don't need to multiply negative 1. But they are all inequality constraints. We need to convert them into equality ones. In this case, we will put slack variables. So what do? We are going to do this. Okay, over here, this is equal. Here actually it's 0 times x2. And for the select variables, I'm going to add x3 right here, x4 right here, and x5 right here. And I want all the x1 to x5, they're all positive or equals to 0. So x3, 4, and 5, they are select variables. When we do that, what happened to the objective function? Basically, 0, x3, 0, x4, 0, x5. That's what happened to the objective function. Nothing happened. But x3, 4, and 5 needs a coefficient in the front. They're just 0. Okay? That's when you add the select variables. Okay? So now let's write everything down in the matrix form. So you are actually solving a new problem. We're actually solving this. So this is going to be your C transpose. This is going to be your A matrix. And this is your B vector. Okay? Now, we're going to pick which one is basic, which one is non-basic. So for the most simple way to do it is to pick up the select variable ones. These are going to be the basic ones. And these are going to be the non-basic ones. Why do we do that? That means we assume x1 and x2 is 0. So it's like we start with x1 equals to x2 equals to 0. We choose x1 and x2 be non-basic. So we choose them to be 0. When you do that, you realize you are only doing this. 111 times x equals to 273. So what are your x3, x4, and 5? They are basically 2, 7, and 3. So you can easily get your x3, x4, and x5. They are basically 2, 7, and 3. So what's your initial guess? Basically 0, 0, 2, 7, 3. That's your initial guess. Did you get it? Anyone okay? Everyone okay? Is anyone confusing right now? Later on you have homework, you know. If you have no idea what I'm doing, you need to let me know. Okay, now, like I said earlier, we're going to check something. We're going to check this particular thing. We need to check this chunk. So we need to do this. So what is my Cn right here? So this part is my C non-basic, right? This part is my C basic. So Cn right now is this, minus Cb is my 0, 0, 0, and AB is basically 1, 1, 1, inverse AN is this. Right? You need to know why this is happening. At the end, you will have -1 and -2. The first coefficient is representing the first non-basic. So this is the coefficient for the first non-basic. This is representing the coefficient for x1. This is the coefficient for x2. If you go back to check on your objective function, basically you have -1x and -2x. Right? -1x and -2x, yes. Exactly same thing. -1x and -2x. So what do? We choose the most negative one. So this one has most negative coefficient. So it will be converted from non-basic to basic. So basically, it was 0, later on, positive. Some positive values. Now what do? Ratio test. Ratio test. So we need to evaluate these two guys. Copy and paste. Okay, and erase some of the things here. And say this is equal, move around. Okay, we need these two. We need to know what is A hat, what is B hat. Okay? So my A hat at this point is going to be, I'm going to reuse this. Copy and paste. It's super lazy. And this part will be copy and paste. So your B is 2, 7, and 3, right? Okay. So at the end, basically, it changes nothing. Okay. And remember, we are doing the ratio test of BI over AIJ. So what is my J? The second one is my J. So only the second one, second column. So this column, this is the J column. So basically, because earlier we chose the second one. So here, this means the second one in your A hat. Okay? So we are doing something like this. 2, 7, and 3 divided by 1, 2, and 0. Okay? So at the end, 2, 3.5, infinity, that's fine. Even is infinity, is fine. And what do? We choose the smallest positive one. This is the smallest positive one. If we do that, at the end, we need to know what is which variable is this ratio test representing. This is representing x3, this is representing x4, this is representing x5. So x3 is chosen. I need to convert from basic to non-basic. That's a finished ending of first iteration. But you feel weird. Hey, nothing happened. Actually, something happened. I will let you know what happened. If I try to do this, try to draw this. Okay, let's try to draw the figures right here. Here, basically, the B heads are 2, 7, and 3, right? These are the B heads. And how about the A heads? Only the J column. So the J column, maybe I keep these so you can compare. Okay. And over here, basically, N is 3. The third one. N is 3. Okay? So let me show you what happens if I plug in the numbers. What are the B's, XB's? Basically, they are X3, X4, and X5. And what are the A heads? The J column. 1, 2, and 0. What are the J XN? The second one was chosen, which was X2. So basically X2. And what are the B heads? Basically right here. 2, 7, and 3. And if you try to draw 3 linear equations, here is your X2. And your X3 was, X3 was 2. X4 was 7. X5 was 3. And if you try to draw the 3 lines that I mentioned, basically this is like this. Oh, sorry, not this one. This one. Okay? And -2 on 7. So here is 2, here is 3.5, and this is like this. Goes to infinity. Right? So when you did the ratio test, what does that mean? It's the ratios are actually what you will get for X2. When you increase X2 from 0 to 2, your X3 will decrease from 2 to 0. So your X2 was 0, now becomes 2, and your X3 was 2, now becomes 0. Do I care about what are the values for the rest? Yes, of course, you can plug in and then figure out what are the values when X2 increases, what X5 remains 5, X4, you can plug in the number and then figure out what X4 becomes. But all I care about right now is X2, you have to become basic, and X3, you have to become non-basic. That's what I need to know for this particular iteration. I don't even need to compute every X. And I'm moving on to the next iteration. So I'm going to do this faster for the next iteration. I'm going to copy this whole thing again. This is going to help me. Okay? And So what will happen if I change some of them into basic, some of them become non-basic? So from now on, I'm gonna do this. Originally, from x1 to x5, it was non-basic, non-basic, basic, 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 right? So it was non-basic, non-basic, basic, basic, basic. It was like that. Now, x2 was converted to basic. So this one become basic. And x3 become non-basic. It was like that. So what is gonna happen is the red circle ones, they are your A, B. And the green circle ones, they are your A, N. For this iteration. Because they swap their duties. So you are going to repeat all the math just like what you did, but some columns become, they have different roles. And the math will change. If you keep on doing this, you realize, hey, you still can, there's something different. Okay, so let's quickly check what's gonna happen. So we're going to do this, copy, and then paste it here. Now, Cn would be, so this would be my Cn. Cn. Actually, transpose, if you want to write the transpose. I should write the Cn transpose. Because I was using dot product. Yeah. I should show you that. I should use this one. So the matrix transformation one. So the matrix form. So when I do this, I should use this one. They're the same thing, okay? So over here, let's use that one. It's better, okay? So continue on. We need a CB transpose. So your CB will be the red circle ones, here and here, okay? That would be your C and B, C basic, right? And then A, B inverse. So what's your AB right now? 1, 2, 0, 0, 1, 0, 0, 0, 1, and inverse. What's your AN? AN now is negative 2, negative 1, 1. 1, 0, 0. Okay. So, I need MATLAB for this. I don't want to do it by hand. Or can I just copy my notes? So I don't need to, let me just copy my notes. Let me see, where's my notes? This. So I already did it in my notes. So at the end, I'm going to be lazy this time. So at the end, you can get negative 5 and 2. So this is the most negative one. And what are they representing? they are representing the two non-basic variables, which are x1 and x3. So x1 is chosen. Next, ratio test. So we need to do this. Copy. Paste. Do this. Copy this guy. Paste. And then move this lower. And then copy, paste. B is 273. If you're done, let me see, what's the solution? Oh, I didn't finish. In my note, I didn't finish. Okay, so I still need no. Let me see. Okay. So 1 0 0 2 1 0 0 0 1 inverse times negative 2 1 negative 1 0 1 and 0. So this is do the same thing, but this time 2, 7, and 3. So 2, 3. Okay, back to iPad. I just used MATLAB to compute, and this is my jth column this time because the first one was chosen with the most negative coefficient in the objective function. Now I'm going to do the ratio test, bi over a hat ij. So it's gonna be 2, 3, 3 over negative 2, 3, and 1, negative 1, 1, and 3. This is the smallest positive. And they are x2, x4, and x5. So this is x2, x4, x5. So x4 was chosen. Next iteration. So if you do it fast, it's not taking a lot of time. We can already move on to next iteration. So x1 become it become basic, and x4 become non-basic. So x1 basic, x2, so bn here, bn, and non-basic. Oh, sorry. So this is a new decision. Okay, so let's circle them just so that we can easily use them. Now compute this guy. So I'm going to do it faster this time. CN, okay. CB, okay. AB, AN, okay. Mela. Okay. Mela. At the end, negative 1.33, 1.67. So this one is the most negative one. That means we still can reduce the objective function even more. And the corresponding variable would be x3 right here. So x3 later on needs to become basic. Okay, do the ratio test. Okay. Copy this whole thing. Oh, sorry. Forget about this. So, the first one is x3 because the non-basic ones are x3 and x4. So the first one has the most negative. x3 needs to become basic. Now I'm going to do the ratio test. And I need MATLAB again. MATLAB. Oops. MATLAB. So I need this part. This is actually the A hat. To iPad. Here, do the ratio test. Now the first column is chosen, so BI over AIJ is going to be 1, 4, and 2 divided by negative 0.67, negative 0.33, 0.67. Only this one is positive, so that one is chosen. And this will be the third basic, so this is x5. Okay? This was, the third x5. It will become non-basic. Final run, I hope. So we are going to do this whole thing again. Copy, paste, and paste those. So now this is becoming non-basic. The third one become basic. So it's easier for you to pick up the matrices. I don't need this anymore. Let's do this. Copy. Almost done with today. Okay, now Cn would be 0, 0. Cb would be this. AB inverse, don't forget. AN. Let's check. Oh yeah, both of them positive. What does that mean? We want the most negative one. There's no negative ones. So now we have coefficients that are positive. So if I increase the corresponding variables, it doesn't reduce the objective function anymore. So we should stop. So it's converged. But what's the solution? Solution would be x, 4, and 5, because they are non-basic, so they are 0. But how about the x, 1, 2, and 3? Thank you. Okay, sorry, converged. So the coefficient is 1 and 2, no more negative, cannot improve the objective function anymore, converged. And because x4 and 5, they are the non-basic, so they remain 0. So the optimal solution for x4 and 5, they are just 0. How about 1, 2, and 3? Basically, you need to solve for this. Solve for this. Then you can get the solution. I'm gonna use MATLAB to help me. Okay, so here, MATLAB, and that is this guy, I think. Yes. Inverse of it times 273. Is that the one? Yes. So the answer would be 3, 5, and 3. So that would be the final solution. But do you even need to know about the optimal solution of the select variables? They're just artificial variables you introduce. So back to your original problem, your optimal solution, all you care about is x1 and 2. So this is what you're looking for from the beginning. Okay, do I have time? Okay, just a little time. I want to make some drawings to help you understand what happened. So I will need to copy the problems. I'm gonna use a graphical approach to help you understand what happened. Okay, so this is going to be my x1 and x2. And because we want all the x remains positive, So it's like there's a wall right here. So everything above and on the right will be feasible. Nothing negative won't be accepted. Then let's take a look at the first constraint. It's a 2x1 plus 2. So here is 2. 2x1 is 4. So this is actually your G1 equals to 0. And if you when you plug in 0, 0, it's feasible. So here is the wall is the wall is like this. Everything above this line is infeasible. Only at the bottom is okay. Okay, this is your first inequality constraint. The second one, 1/2. So 1/2, 3.5. So it's right here. 1/2. Yeah, 1/2. So it's like this. Plug in 0, 0. Okay, so it's like this. So this is your G2. On the line is G2 equals to 0. So that will be your second. Everything below would be your feasible space. And over here there is x has to be smaller than 3. So it's like there's another wall. This is your, when x1 equals to 3, that's the straight wall. On the right hand side, it's not allowed. Only the left hand side is okay. So from here, you can tell it's a feasible space like this. Did you remember where did we started? 0, 0. So what happened was we started from here. That's our initial guess. Okay? And what did we do for the first iteration? We wish x2 become basic. So we want x2 become positive. So what happened was we started to move along this line. And we actually end up with this corner. It's 0 and 2. Did we have x2 equals to 2? Here, I said x2 equals to 2. We stopped there. Because if we keep on moving along the x2 direction, and we want to stay inside the feasible space, the most we can walk would be stopping at 0, 2. If you go further, everything becomes infeasible. Okay, so what happened next was we actually moved along this boundary. But moving from this point to this intersection point is not by increasing x1 or x2. It's actually increasing one of our slack variables. So one of our slack variables, which cannot be shown in here because this is just a 2D drawing. Our slack variables are in the 3rd, 4th, and the 5th dimension. One of it was 0, and by increasing that slack variable, we would be able to move from 0, 2 to this new point. This new point will be 1 and 1 and 4. 1 and 4. So let's get back to our second iteration and check, did we advance one of our slack variables from 0 to positive?
So in the second iteration, the one being chosen was I'm sorry. It's actually x1. We increase x1. But when we increase x1, so I was wrong. If I only increase one of the select variable, how can we move? Actually, sometimes yes. So in this case, x1 was chosen as the one to have increment. So x1 was 0. What I said earlier was wrong. In the second iteration, x1 was 0, and we decided to increase the value of x1. But when we do that, we will be moving towards some direction. In fact, it's going to move along this boundary. Okay. In the third iteration, I think we were increasing one of the select variable. So second iteration was x1. The third iteration, that was the time we actually increased x3 from 0 to certain value. And that was the time we actually moved like this. So this is increasing x2. This was the time when we increase x1. And this was the time when we increase x3. And when we are here, we can no longer increase any variable because we are like to the tip already. And if we take a look at the objective function, try to draw a contour of the objective function, you will realize one thing. If I plug in 2 and 1, that's -4. 2 and 1, this is -4. And if I plug in 0 and 2, okay. So this is my the contour looks like this. This is the direction if we take the gradient, negative gradient. If you look at our objective function f, if I take the gradient, it's gonna be negative gradient. It's gonna be 1 and 2. Remember in Newton's method, we try to move along the negative gradient direction. This red arrow is the direction of 1 and 2. So actually, moving toward this direction is the direction that goes to the bottom, goes to the minimum of our objective function. The situation is, in the past, we don't have constraints. There's no walls. We can keep on moving along the steepest direction or new conjugate gradient direction. But now there are walls. We cannot penetrate through the wall. So what linear programming did was, every time there is an intersection, it will make a decision, do I go left or right? And what will happen is, at the beginning, if I move left or move right, actually move up or right, if I move up, it's steeper. The objective function value drops faster. If I move right, the slope is not as steep. That's why linear programming chose to move up, because at the beginning, if I move up, the object function is supposed to drop the fastest. However, because there are multiple intersections, you need 3 iterations to stop. If you go right, actually 2 iterations, you will converge. But as an optimization solver, you should not know what's going on. You just need to follow certain procedure. The idea is, wherever you are, move toward the steepest direction until you reach the wall, reevaluate again, move toward a different direction, which have your object function drops the fastest. Keep on doing this. That's the idea. Okay? Now, it's time to give you a homework. So let's try to say, you want to do a 2D problem or 3D? Let's do a 2D right now, 3D for example. Or you want to practice 3D now? It doesn't matter, because my grading speed is so slow, you don't know the solution. Let's practice 2D for homework. So I'm just to randomly giving a problem. Okay, so what I want to do is, I'm going to give you a problem like this. No, I should try different ways. I want to do something like this. Yes. So if this is the case, I'm gonna do this. Okay. So this one. This one. Okay. Double checking. Quickly double check. Easy contour. Yep. Ooh, no. And let's see. Okay, we'll see. But no. Not that's fine. Oh no, not fine. I forget to hold on. Okay, good. Then the other one. Okay, that's fine. The third one. Oh, and then okay. Huh. Right? This one is wrong. Let's see. It should be plus. Should be plus. Okay. Okay. Is this problem solvable? Okay. Too easy. Too easy. 2 iteration converge. So I need to. Which one is that? So I should go this way. I should go this way. So I don't like the last one. I should go that way. So if I go that way, maybe 7x minus 20. No, minus 40. Okay, so solution is right here. Good. So that was okay, good. Now this one. Double checking if I'm doing this right. Close everything. the objective function, this, okay, hold on, okay. The first plot should be positive 1/2. This one's okay. Next one, this one. Double checking. Yes, this one's okay. The last one would be 7x, this one. Okay, and then, there's the figure. Here. Okay, should be solvable. Now, let me see which one is which one. So this should be, okay. Second one is this one, so okay. Yep, the third one should be this. Okay. Okay, good. Okay. So this will be your homework. Don't need this anymore. Try to solve this using linear programming. So if anyone solve this and then figure out, hey, something is wrong, send me a message. Maybe I missed some of the symbol. Okay, this is your homework. About the course schedule, are we doing another exam again? Is it too much?
Too much.
Optimization. Based on the progress, today I assign, so this is your homework 4, right? And I collected your homework 3. Because we are 1 week ahead, we are actually 1 week ahead, maybe we can postpone all of our exam activities. So next week I will show you how linear programming works in MATLAB, and I will continue on unconstrained optimization. But so once you're done with the homework, if you have questions, you can ask me the question next week. So we can do the exam next Saturday. No, but this week, if I finished grading exam 1, we can do the makeup exam. Yeah. So I need to push myself to finish the makeup exam, to finish the grading. Okay? So that's it for today. Thank you.